So this is section 4.3 in our book. We're going to graph exponential functions. So we're talking about things that look like y equals a times b to the x. And so we're going to kind of compare and contrast these, try to get a feel for what the a does to the graph, get a feel for what the different b's do to the graph, and get a mental picture of that. So a and b are called parameters. So in the language of math, the idea is that the variables are x and y. That is, within a single problem, the x and y changes, and we know that our domain for exponentials is all real numbers, and the range, it depends. We'll see. We'll talk about a little bit of that down the road here. But for the a and b can be chosen to be different things for different problems. Once you're in a problem, it stays, but from one problem to the next, it can vary. So those are known as parameters. We know that a, we said, is sometimes called the initial value. So in terms of, in the context of actual problems, models, if we're trying to describe a situation, maybe a population growth or the value of, say, a car or something like that, then the a is going to be the value you get when x is 0. So that's like it's your starting point, the initial value. In terms of the graph, that's going to be the y-intercept, even though we don't usually call it that. So that's what it's going to be. And the b is going to be, we call that a growth factor. And we know that it holds within it. It's going to be our 1 plus r, which, if the r is negative, so if b is less than 1, then that r is negative, and so it's a decay, it's going to decrease. And if the r then is positive, or the b is bigger than 1, then it's going to be an exponential growth function. So what I want to do here is we're going to graph a few of these on the same axis so we can get a better comparison in terms of what is the b doing. So we're going to graph y equals, and because I have all these great colors, I'm going to use different colors here. So let's do y equals 2 to the x, y equals 5 to the x, and y equals 10 to the x. And we're going to graph those on the same xy axis, and then just kind of talk about what that b is actually doing, and kind of get a picture in your mind anyway, so that when you see an exponential down the road, we kind of have an idea of how they're going to compare to each other. So if we plug in, say, 0, then 2 to the 0 is going to be 1. And if we plug in 1, then 2 to the first is 2. And if we plug in -1, then 2 to the -1 is what? 1/2. Very good. So it's going to be right here. So it's going to do something like this. So there is our y equals 2 to the x. Now we notice that as you go way out there to the left, it's getting closer and closer and closer to the x-axis. It's never actually going to touch the x-axis, and so we call that a horizontal asymptote. So it has a horizontal asymptote at 0. As we go to the right, and you put in bigger and bigger numbers, this thing just takes off and gets huge. And we talked a little bit before that no matter what kind of a straight line, in fact, no matter what kind of even a parabola or a cubic or any power function, this is something we spend a lot of time on in AP Calculus next year in the fall, right about now, is that we see that any kind of power function, x squared, x cubed, x to the fourth, it may get bigger than an exponential initially, but down the road, an exponential is going to outpace it, and eventually it's going to catch up to and get much bigger, much faster. So we will call this a higher order magnitude function next year. Now 5 to the x, when you plug in 0, it's going to share that 0.01, so it also goes through that point. When you plug in 1, we're going to be up to 5, so it's going to be somewhere in there. When you plug in -1, it's going to be 1/5, and 1/5 is smaller than 1/2, so it's going to be closer to the x-axis than the y equals 2 to the x curve. So you get this kind of, split, and what happens on one side of the y-axis or the other. So we're seeing that when the base is bigger, when the base 5 is bigger than the base 2, that to the right of the y-axis, the higher base is above the lower base. It gets bigger faster. At 0, right on the y-axis, they're at the same place. And then to the left, the bigger base, the 5, is going to get closer to the x-axis faster. It's going to hug that x-axis faster. And the same thing is true then when we plug in the 10 to the x. Again, it shares that same point at 0, 1. And then to the right, 1 is going to be way up here at 10. So it gets really steep really fast once it crosses the y-axis. And on the other hand, 10 to the negative 1 is 1/10. It dives down close to that x-axis even faster. So I don't know, the way I remember it, and I just share this, but you can find some other way. The way I think of it is when you're looking at this y equals b to the x, because we've chosen the a just to be 1 here to simplify things and just focus on what the b is doing. What, in my mind, I'm thinking is that it's going to have that basic exponential growth shape. You got that asymptote to the left of the x-axis. It's going to bend up and get big fast, but the bigger the base, the closer to like a right angle it tries to be. It grows faster once it crosses the y-axis, and it hugs the x-axis quicker to the left of the x-axis. Now, it's never going to be a corner point. It's never going to be a right angle, because it's always going to be a curve. It's going to be bent there. But in my mind, the bigger the base, the closer to a right angle, and the smaller the base, then you kind of tip it this way, away from the x-axis a little bit more, and it flattens out a little bit more there. Okay? So similarly then, if we look at, you see it if I move it over here? So if we do the same idea, but we look at the fractions. So if we do, say, y equals 1/2 to the x, which if we think about it, 1/2 is 2 to the negative 1 power. And so that's 2 to the negative 1 to the x, which is going to be 2 to the negative x. So y equals 1/2 to the x is really the same thing as y equals 2 to the negative x. And similarly, y equals 1/5 to the x is the same thing as 5 to the negative x. You with me there? Okay, and in a similar way, then y equals 1/10 to the x is going to be the same thing as 10 to the negative x. And we know what the negative exponent does. So when you have a graph and you have that negative, if we look at the 2 to the x that we started with right here, then how does that compare to y equals 2 to the negative x? Or maybe I should say, how does y equals 2 to the negative x compare to 2 to the x? It's going to be flipped over the y. Exactly. So what you're going to get then is, if this is our 1/2 x or 2 to the negative x, then it's going to be a decay. So you can see that either because you have the base is less than 1, which is going to make it be a decay curve, or if you look at it as a reflection of the growth curve 2 to the x in the y-axis, that makes it into a decay as well. So they're consistent. It's saying the same thing. And similarly, the 1/5 is, is going to take off quicker to the left and hug the x-axis faster to the right of the y-axis here. And in a similar fashion, 1/10 or 10 to the negative x will be steeper still in its decline to the left of the y-axis and will decrease faster and hug that x-axis closer, faster than when it's to the right of the y-axis. So once again, in my mind, even though it's never going to be a right angle, I think of it as, in this case, you can either think as the base getting smaller because 1/5 is less than 1/2 and 1/10 is smaller than 1/5, or as our base is bigger but it's being reflected, that growth curve that we're reflecting, then it's going to become closer to that right angle. It's getting steeper on the left side, where it is steeper as it falls, and it's hugging the x-axis faster there. So it's important to keep an idea of that, to have kind of an understanding of what's going on there in terms of its graph. So that's the B part. So then we want to take a look a little bit about what does the A do. And so let's compare an exponential with some different values of a. So this time, I'll pick, again, we'll start with our y equals, I'll emphasize the fact that we're looking at the a. So this is 1, let me write it maybe this way, 1 times 2 to the x. So the a there is our 1. And then we'll do y equals, say, let's say 3 times 2 to the x, we'll do in the blue. And then we'll do y equals, and we'll say 1/3 times 2 to the x in the pink. So we're going to see here what the different a values do to the graph. And this is maybe a little more subtle, I don't know. So 2 to the x is still going to be like we've seen at 0. 2 to the 0 is 1. When you plug in 1, we're going to get 2 to the first is 2. And when you plug in -1, 2 to the -1 is 1/2, which is a half. So this is kind of our basic, kind of like a parent function here. So this is our standard basis of comparison. So then on the next one, when we have 3 times 2 to the x, the big thing is when you plug in 0 for x, 2 to the 0 is still 1, but that 1 is now going to get multiplied by 3. Now this is not a translation. So you're not going to take this identical curve that we're looking at here and move it up 3. That's what we would get if we had, say, 2 to the x plus 3. This is, in the words that you would use in geometry, this graph and the orange graph we have here are congruent. They would fit exactly on top of each other, but we just slide one up. That is not what's happening here. In this case, whatever value we're getting for 2 to the x, whatever that height is at various times, that height is going to get multiplied by 3. And so it's not going to be, when we graph this, if we tried to slide it down on top of this, it would not be a perfect match. Okay, they're no longer going to be congruent. So we're going to be at 1, 2, 3 is going to be where this is. Now these really small values here are going to be 3 times as tall, which means they're not going to be very tall. But these big values here are now going to be 3 times as tall, so they're going to get stretched even more. I'm trying to see if I can try to make that look like what I want it to show. So the spacing between these is changing as we move across the graph from left to right there. So they're no longer congruent graphs. The blue is a vertical stretch. What we will do is try to keep an eye on, what I'm going to ask you to do is to keep an eye on what happens to the asymptote as you do these different things, stretch, shrink, reflect, translate. Where does that asymptote go? Where does this initial point that started at 0, 1, where does it end up after all of the changes, the transformations? And then what is the basic shape? Is it going to be a growth? Is it going to be a decay? Is it going to be reflected in the x-axis growth or reflected in the x-axis decay? Those are kind of the choices that we'll be looking at there. Okay, and so then here, when we multiply by 1/3, again, 2 to the 0 is 1, times 1/3 is going to be 1/3. So now we're going to cross the x-axis at 0, 1/3. Now, each of these heights that we see in the orange as we work our way from left to right is going to get multiplied by 1/3, so it's going to be 1/3 as tall. So it's going to be a little flatter there. And each of these heights here is going to be 1/3 as small as well. And so it's going to do something like that. So I think I can show it a little bit better on the pink curve compared to the orange that I maybe do on the blue. But they are no longer exactly the same shape. They're still growth curves, but they're not going to be, it's not like you can just slide the pink on top of the orange and get a perfect fit. Okay, they are not congruent any longer. Okay, so the smaller A is going to be then a shrink, a vertical shrink we would call that, and a larger A there is going to be a vertical stretch. And in particular, we're going to watch what's going to happen to that point where it crosses the y-axis, and then where does that move. Okay, so with that, I want to talk a little bit more about this idea of a horizontal asymptote, because we see in these exponential growth and decay curves that they are going to have a horizontal asymptote. So we're going to talk about this a little more formally, about what a definition is mathematically of a horizontal asymptote. And we're going to introduce some symbolism that will serve us well in the future, not just when we talk about exponentials, but when we talk about other things, especially a lot of ideas we'll talk about next year. So we're going to talk here about horizontal asymptotes. And I will abbreviate these because I get tired of writing out horizontal asymptotes all the time. So I'm going to call that just an HA. And then we'll also talk about vertical asymptotes, and I'll abbreviate them as VA oftentimes as well. So our book, just to kind of warn you, our book is kind of trying to transition you into the formal notation that is really used in math. And I'm not going to use their notation because I'm just going to jump right to what is actually used all the time. But I just want you to see what you're going to, familiarize you with what you're going to see in our book. So our book says they're going to use the notation and they'll write it this way. F of x approaches k as x approaches infinity. So that's the way they are going to write it, in that kind of horizontal line like you see it right there. But they will only do that for a little while, for maybe a couple of sections, and then eventually they're going to transition into what is actually used in all of the rest of the mathematical world. So we'll just jump to it right now and not do the transition. So no training wheels for you guys. You're going to just jump right into the deep end of the pool right off the bat. So we will use, for this notation, we're going to say LIM and then x arrow infinity down below. And then we'll say f of x, and we'll make that equal to k. So the way we will read this symbolism here is the LIM means limit. The x arrow infinity means as x approaches infinity. So the limit as x approaches infinity of f of x is equal to k. So that's how that is read. Limit as x approaches infinity of f of x equals k. And we'll do this also down the road here, not too long. We'll use this not always as x goes to infinity or negative infinity, but as x approaches other numbers as well. But this symbolism, that'll be a mainstay. So we'll see that a lot. So what we say then, what we mean then, is if this approaches k, we're talking about in our curve, whatever our graph does, and we're talking now about exponentials, but this will extend beyond just exponentials, as we'll see. So if the limit as x approaches infinity of a function f of x is equal to k, that means that when we go way out there to the right, when we go to positive infinity, when we plug in big values for x, and I'm talking like 1,000, 1,000,000, 1,000,000,000, whatever, way out there, infinity goes a long way to the right, then this is approaching the line y equals k. And so that means that way out there to the right, this graph, whatever the curve does in here around 0, around the y-axis, I don't know. This makes no claim. But we're saying as we go way out there to the right, this is going to get closer and closer to that horizontal line y equals k. So it may be that the function does, I don't know what, in here, but then eventually it kind of settles down and it approaches that curve, that y equals k from above. It may be that this does, I don't know what, over here. It makes no claims. It might cross that horizontal line any number of times, but eventually it's going to settle in and get closer and closer and closer to that horizontal line. That would still be what that is describing. It could be that this thing does, I don't know what kind of goofy thing over here, and then maybe it's going to cross that horizontal line a whole bunch of times, but it does it in a way that is still getting closer and closer and closer and closer to that horizontal line. Okay, that is still true according to what that's saying. Because as you go out there to the right, the curve is still getting closer and closer to that y equals k. It could even mean, oh, there's my purple when I need it. It could mean that the curve actually becomes that line y equals k. So maybe this does some goofy things for a while, but then it settles in and it just actually becomes that horizontal line. All of those graphs here fit with what this is saying, with the limit as x goes to infinity is equal to k. That make sense? And all of these we are going to call a horizontal asymptote. So all of the functions that I have drawn here have a horizontal asymptote of y equals k. Okay, so there's our definition, sort of. So if the limit as x goes to infinity, I'll say, I'm going to write it this way, either as x goes to positive or negative infinity of f of x. So if we go way out to the right and this approaches a single number, that's going to be an asymptote. If we go way out to the left, as x goes to negative infinity, this approaches a single number. If that is equal to k, then what we say is y equals k is a horizontal asymptote. A lesser athlete would have dropped that. Okay. So now we are going to talk about this to start with in the context of exponential growth and decay curves. But we'll extend this. It'll be a while, but we'll talk about this a lot also. We're going to do what are called rational functions. And so we'll look at those probably more around like January or February in there. And then we'll also next year talk about things that are even more exotic than that. So we will, like next year, talk about, and a little bit once in a while, but not very much here. We can even have, we can have curves, functions that have, well, we'll see exponentials have horizontal asymptote in one direction and no asymptote in the other direction, or even a horizontal asymptote in one direction and a different horizontal asymptote in the other direction. That is possible as well. So we're talking about this in the context of exponentials, particularly exponential growth and decay. So let's see how we can use this language and symbolism to talk about that. So if we talk about the limit as x goes to infinity of, say, 3 to the x, and we're going to look at the limit as x goes to negative infinity of 3 to the x. So first we have to just fight our way through and get familiar with and learn the symbolisms. What does this mean? And then if we can get past that hurdle, then what's the big concept behind this? So what do we mean by this limit idea? And what does that mean in terms of horizontal asymptotes with respect to the graph? So there's kind of a few different things going on. So with your finger in the air, what does the graph of y equals 3 to the x look like? Yeah, we talked about it. So it's exponential growth. So we know this already. So we know that this is going to do something like that. So there's our curve y equals 3 to the x. And sometimes it's nice when we're just getting familiar with the notation and symbolism to have this in the background. Other times we may use this in order to get the graph. So we may do this kind of analysis in order to get the graph. So if we go way out there to the right, the limit as x goes to positive infinity. This curve, what are the y values approaching here? Are they getting closer and closer to a single number? No. We would say they are growing large without bound. We could say that they are approaching infinity, but remember, infinity is not a number. Right? It's gonna, if you pick a billion, it's gonna go past a billion eventually. So we would say here, the limit is infinity. And because that is not a finite number, then that means there is no horizontal asymptote going out to the right. Does that make sense? The connection between the limit is not a finite number, and this doesn't have a horizontal asymptote there. Now, the limit as x goes to negative infinity, as we go way out to the left, now the y values are getting closer and closer to what? 0. And so that is a finite number, and so we say then y equals 0 is a horizontal asymptote. Y equals 0 is a horizontal asymptote for that particular function. So even if it's only an asymptote in one side, like we're going to see in exponentials, it still qualifies as being what's called a horizontal asymptote. Okay? So if we do something like, say we do the limit as x goes to infinity of, and then we have 1/2 to the x, then we're going to talk about the limit as x goes to negative infinity of this 1/2 to the x. And lurking in the background is the graph, but let's see if we can talk about it first, maybe without referencing the graph, and just think about this. So as you put in bigger and bigger positive numbers, you know, what happens when you take a fraction, something that's less than 1 times itself, so a half times a half is a fourth. And is a fourth bigger or smaller than a half? It's smaller, right? And so each time you multiply by a half, you get something that's half as big. So it keeps getting smaller. Now, if you do that over and over and over again, 100, 1,000, 1,000,000 times, then this is going to get closer and closer to 0. And that's what we mean by a limit. It doesn't have to actually ever equal that. It is just getting closer and closer to that number. So we say that is 0. And because that's a finite number, we say that y equals 0 is a horizontal asymptote for the graph y equals 1/2 to the x. And likewise, if you put in negative infinity, so when you plug in like a -1, the negative part's going to flip it and make it 2. So I'm making an algebraic argument rather than referencing the graph. So -1 is going to flip that and make it 2. -2, you're going to flip that from the negative part. Squared is going to be 4. And so as you put in bigger and bigger negative values, this is going to get bigger and bigger. And so we will say its limit is going to be infinity. And since that is not a finite number, then this is not a horizontal asymptote to the left. So, okay, so we got this horizontal asymptote. And of course, we know that 1/2 is going to be this decay curve. And so you can see that horizontal asymptote, you can see that limit going out to positive infinity is going to be 0. Okay. So that's the formal symbolism and language, vocabulary of limits and horizontal asymptotes. So now we're going to solve some equations using our graphing calculator. So if you have one, bust it out. If you don't have one, I have some rentals that come with very good rates. So in that suitcase over there, you can find one. So we're going to solve exponential equations. Graphically. Okay. So we have one equation is y equals 3 times 2 to the x, and the other one is going to be y equals 25, and we want to find out where these two intersect. What is a solution to these two there? So we haven't talked about logarithms, even though you've done that already in your Algebra 2 days. We will talk about that shortly. So we can solve that using logarithms, and we can talk about that. I'll go over that here in a moment. But a skill that we want to have is how to do this on our graphing calculators, where we're going to graph this one as y1, we'll enter this one as y2, we'll graph them. We may have to play around with the window. What's the x min, x max, y min, y max, until we can find that point of intersection and come up with those, and there may be even more than one sometimes, point of intersection to solve that. Because then we're going to also, I'm going to show you shortly, one that we can't do with logarithms. It's just too complex. And so, well, we could, I don't know if we even can. So we'll talk about how we can need to have that calculator skill. So I'm gonna, and I will do this sometimes, I'm gonna choose a window to go, when I write this notation, 0, 10 in brackets, and then I'm gonna go 0, 3. So I'm always telling you, this is the X window followed by the Y window. So this notation means I'm telling you what to use for X min and X max, and what to use as Y min and Y max. So we're going to enter this into our calculator, Y1, Y2, put our window onto there, and then we'll talk about how to find that point of intersection. I'm going to pause this for a moment and switch the view and get my calculator. So here, not too bad. So we have, there is y1 is equal to 3 times 2 to the x, y2 is 25. I'm going to change the window so we go 0 to 10, the x, and we'll go 0 to 3 on the, whoops, the 0 to 3 on the y. So now when we graph this, we're going to see, here's first our exponential. I don't think I chose a good window because 3 times 2 to the x. Let me change that around. That's not a good choice. Let me instead make this 10. I don't know where I got what I got there. We may have to adjust this. Okay, my second try, there's the exponential. Oh, that's not going to be close. I think I want 30 because we got y equals 25 as 1. That wasn't a good choice at all. I'm going to choose the y max. Let me try 30. And then because what I'm going to do for the y scale is right now, if I go to 30 and the tick marks are every 1, it's going to be so many it looks like a fat y-axis. I won't have to put my y-axis on a diet, so I'm just going to call that 10. So the tick marks are every 10. So that'll look a little cleaner, hopefully. So here's our exponential. And where's our y equals 25? There it is. And now we can see where that intersection is. So the way you do it on the calculator is we're going to go to second trace. That's the calculate menu. So second trace gets you to there. Okay, tell me if you're not to that place. And then we want to do intersect, which is that 5th option. So we're going to do the intersection of those 2 curves. When I hit enter, it's asking the question, is this y1 the first curve? Yeah, so I just hit enter. Is this y2 the second curve? Yes, so I'm going to hit enter. And then guess, you can just use the right and left arrow. Here it won't really much matter because these functions behave pretty nicely. But if you had something really wild and crazy that maybe had some vertical asymptotes or discontinuities, then sometimes you have to get the cursor pretty close to the point of intersection, or it may send you careening off who knows where, and you'll probably still get an answer, but it may not be what you want. Then we just hit enter, it does all the work, and so we can see that the x value is what we're looking for there, and we'll round to 3 decimal places, so that's going to be x equals 3.056. So x is equal to 3.0. What's that? Yeah. 0.59, thank you. That sounds better. Okay, so far. Okay, so that one now we can solve pencil and paper. We still have to use our calculator. Let me come back to this one because I've got the video here. Let's do a problem that we have to use our graphing calculator for. So let's see if we can find the intersection. Find the intersection of, and we'll say y equals x plus 2 and y equals 2 times 3 to the x. 2 times 3 to the x. Okay, so we may have to play around with the window here, but let's come back to our calculator, go to y equals, and now we're going to change what was in that first y1. I'm going to call that x plus 2. Then I'll drop down and clear off that old one and put in 2 times 3 raised to the x power. Okay, and let's see, let's maybe change our window here. I think if we do something like maybe -5 to +5, let's start there for the x's. And I think for the y min, I'm going to maybe go -1 so I can see the x-axis a little more clearly. And I don't think we'll need too much. I'm going to go to 10 right here, and I'll make the tick marks be just 1 again like they were originally. And we may have to adjust this. Let's see what happens. So when we graph this, here's our straight line, and then here comes our exponential. And so we can see there's actually how many places where they intersect? 2. So it sure looks like the first one is at 0, 2, or that one on the right is 0, 2. I think we can confirm that, right, just without our calculator. So we don't have to actually use our calculator to find that intersection. When you plug 0 into y equals x plus 2, we're going to get y equals 2. When you plug 0 in for the exponent, 3 to the 0 is 1 times 2 is 2. So 0, 2 is clearly one point of intersection. We can get that. Now the other one we're going to need our calculator for. So see if you can remember the steps there and see if you can find that point of intersection. I'll give you a chance to start on it, and then I'll repeat the steps if you need it. So we're going to go second trace down to option 5, which is intersect. I'm going to hit enter because the first curve is correct. Enter again because the second curve is correct. I'm going to go left arrow and move that cursor down closer to where it looks like those are going to intersect. Hit enter, and I'm getting negative 1.68. I think that's 6, negative 1.686. Is that right?
Yep.
Okay, negative 1.686. Any questions on that? How we're doing that? Okay, let me see if there's anything else I want to do with the calculator. Yeah, let me do another one here. So we'll say here's going to be a word problem. So let's see if we can resolve this. What am I doing on time? Okay, so let's say a 200 milligram sample, a 200 milligram sample of carbon 14, which we'll abbreviate as C14. This is a radioactive material. Decays according to, so it decays according to this equation, the Q of T, the quantity at time T, is equal to 200 times 0.886 to the T power. And what we want to know is when will 20 milligrams remain? When will 20 milligrams remain? That makes sense?
Mhm.
So what's our strategy? Anybody? Oh, we're on it already. So what do you want to call y1? We're going to do this on a calculator. The Q of T?
Mhm.
So that's going to be the 200 times 0.886 to the, we'll call it x. And y2 is going to be the 20. Okay, and then we'll have to play around with the window to find that intersection. So I'm going to clear that old one off, and I'm going to put in 200 times 0.886 raised to the x power. Clear off the old one, put in 20. Let's see, for a window, any good ideas? Shall we try, for X-Men, we can go 0, I think. I don't know what this is going to be. Anybody finding anything?
I just said 25.
25, and that worked?
Yeah.
So, and I'm going to make the scale tick marks 5, so I don't have to get 25 little tick marks in there. I'm going to go for a Y-min. I think I can go 0 now, and we want to know when's it going to be 20, so I'm just going to go 30 and make the tick marks 10. Okay, so here's the graph. Somewhere we're going to see our exponential decay. There it is, way over there. And here comes our y equals 20. We caught it, so that's nice. So we can then do our second trace for calculate, find the intersection, and the first two curves are right. Move the cursor over a little bit and hit enter, and it looks like it's 19.024. Does that sound right?
Mhm.
So 19.024, and we didn't really say what the time is. I'm going to assume here that's going to be in years, but I don't really know. Okay? Okay. So I'm going to try to quickly here do an exponential regression equation. So I'm going to see if we remember how to do this. Find an exponential regression equation, and I'm going to give you a table of values here. So I'm going to say T, and we're going to have P. So the T values are going to be 0, 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. And the Q values are going to be 1583, 1583 at time 0, 2183 at time 10, 3122 3767, 3767 at time 30, 4715, 4715 at time 40, and 5947, 5947 at time 50. And we're going to try to come up with an exponential regression. So it has been a while since we've done a regression, and I don't know if we've ever done an exponential. So see if we can remember the buttons we have to push here. So remember stat, hit the stat button. Okay, and then you're going to hit enter. And I got a bunch of junk in mine. So I'm going to up arrow into the formula bar, and I'm going to go clear, enter, and that'll wipe that clean. I'll go left arrow and then up arrow, clear, enter to wipe that clean. So in the L1, we're going to put our time value. So 0, 10, 20, 30, 40, 50, 0, 10, 20, 30, 40, 50. Go right arrow, and we're going to put in 1583, 1583, enter, and then 2183, and then 3122, and then 3767, and then 4715, and then 5947. Okay, now we're going to go back to the stat button, right arrow to calculate, and now we're going to do a search for exponential regression. So I'm going to scroll down, so there it is, option number 10 is exponential regression. So I'm going to hit enter, and go down to the store regression equation, and we're going to put that into variables, right arrow, enter, enter for Y1, drop down to calculate. You with me? Katrina, you with me? Okay, then hit enter, and it works its magic. And it has copied all of that into Y1, so it's there for us. Okay, and I lost my values there. So I'm about out of time here anyway, but remember when we go to...
Sorry, how do you calculate it into, or how do you get it into Y1? It's already, I'm not, oh, mine is.
So do you have, so when you go stats, calculate down to option number 10. So when you hit enter, you have to drop down to store regression equation and put in Y1.
Oh, okay.
So then you're going to go variables, right arrow, enter, enter. So when we actually do a computation, remember, you'll write down your rounded values, but you'll use Y1 of to actually plug in numbers. So,
Ray Mueller,
yes.
Madison Terrell, will you come to the counseling office?